In this video, I'm going to talk about transformers, the T in ChatGPT. And this is a minimal transformer to clarify what's going on. I'm going to go through different parts of it, and not the whole thing, probably, but just to clarify what some parts mean. So scroll down through it real quick, and scroll back up. Okay, start from the top. So this imports Torch, the PyTorch module. This imports the torch.nn or nn functional as f for plotting or making plots, graphs, etc. matplotlib. This is getting the file that's called the Tiny Shakespeare, which is approximately 1 million characters of Shakespeare. This is grabbing that file, and this is putting the training on a GPU if it's available. Otherwise, it puts it on CPU, or that allocates this or gets the device variable to point to that. Then it says if it's CUDA and if bfloat16 is supported, then the data type's torch.bfloat16. If it's CUDA, or else if it's CUDA, in other words, not bfloat16, then use float16, and else use float32. The float32 is for if it's for CPU, then it uses float32 if CUDA is not available. So the float16, what that means is there's 16 bits. Bit is the transistor, if it's in DRAM, transistor that's charged or discharged, a capacitor that's charged or discharged. And bfloat16 is a way it's structured, so there's not as much waste when it does computations. So because it doesn't have to be as extremely precise like a regular float16, and so it uses this, and that helps with the computations to be more efficient. It's kind of a combination, I guess you'd say, of float32 and float16. Has some of the benefits of float32 and some of the benefits of being 16 bits like a float16. So this just prints what type of device. This is the config. Here's the learning rate, which in this case is set to 4e-3, which is 4 times 10 to the negative third power. This is how many training iterations to go through. This is the batch size, number of dimensions, which is the number of floating points inside each vector that represents each token. In this case, the token is represented as a single character, such as the letter A, lowercase, or a / or whatever the character is. So this dimension, what it means is that it would have 64 numbers representing each token. So just say the letter lowercase a, it would have 64 numbers representing that, and they would be of type bfloat16, float16, or float32. So this next part is the number of the number of heads inside an attention layer contained within an attention block. There can be things called heads, which can process different parts of data at once. And this says the head's dimension is the total dimension 64 divided by the number of heads. So 64 divided by 4 is 32 divided by 2, which is 16. So each head would have 16 floats in it. And number of layers, a layer is a transformer block. The transformer blocks contain attention layers, multi-layer perceptrons, and normalization layers. So this contains 4 attention. This transformer has 4 transformer blocks, and each one of them has attention, multi-layer perceptron, and normalization inside them. And each of the attentions have 4 heads in them. So this is the MLP dimension for the multilayer perceptron. It was 1024. What this means is that you have inputs, but in this case, the next layer, like if you picture the dots and the next layer's another set of dots, and all of them are connected by lines, like when you look up a neural network, this is like the middle thing, how many dots there are. And this is the block size. Let's see. Evaluation batches. This is for the evaluation metric stuff. Show plots equals true. This is for plotting the stuff. It's for mechanistic interpretability, like I believe these two are. That's if you want to look inside kind of what the AI model is thinking and so on. So this opens the input text that was downloaded from up here. And assigns it to here. This sorted, what it'll do is it'll take that text and it'll put it in a set. A set has uniques. So it'll find every character in that set and it'll only include one of each of those characters. And then it sorts those in order, just say like alphabetical order. So that way, in that text of 1 million characters of Shakespeare, there's probably lowercase a, lowercase b, etc., all the way to lowercase z. And then there may be quite a bit of uppercases also, and so on. So this will sort from A to Z. And then go down here. This is the vocab size, or the vocabulary size. In this case, it's however many characters there are. And just say like 26 uppercase, 26 lowercase. So that's 52 characters. And just say if there's 5 other characters, such as exclamation marks, periods, commas, etc., then that'll be 52 plus 5 is 57. And I forgot how many are actually in here. I think it's like 60, somewhere in there, 64 maybe. And then here is the string to int. So it'll take the string character and convert it into an integer. And this is the int to string, so it can be converted back. This is encoding. It's using the, let's see, the S. Where is S? Let's see if I can find it real quick. Oh, sorry, it's right here. What's the lambda? So I think it's used down here, if I remember correctly, somewhere. So anyway, what this does is it encodes it, and this is for the decoder. This tells the vocab size, dimensions, and the number of layers. Remember, the layers is the same thing as a transformer block. So this splits the data to train, validation, and test sets. 80% train, 10% validation, 10% test. So this encodes, oh, here we go. This encodes the text. So text goes in here, and remember, text is this full 1 million characters. So it goes in the encode, which is here. And this will iterate through it'll iterate through every one of the 1 million characters in that Shakespeare. And for each one, it'll pass it in this S to I. Remember, S to I is up here, and the string to int. So it'll convert it to integers so the AI can process it better. And at some other point, it would use the decode. Could use the decode to turn it back into strings again. Let's see the empty string dot join these. So that's part of the decoding. And go down here. This says device equals device. And remember, the device is either CUDA with bfloat 16 or CUDA without bfloat 16, which would just be it'd still be the CUDA either way. but if CUDA is not available, then it would be a float 32 on CPU. So if we go down here, where was it? Device equals device. So now go to here, that's telling the length of the tokens, and go down here, train the token, or these are the training tokens. Oh, this is the splitting, the train, validation, and test. So it's for the 80% for the training, and then it starts at that training spot at 80% and goes to 90%, which is a 10% difference. So that would be for the validation tokens, and then same pattern for the test tokens, goes up to n. So, it would be the percentage of that. So if we go to here, that tells the length of the train, validation, and test. Then this is a sliding window per token. So the idea of how the transformer works, I'll stop right here for the moment. The idea of how the transformer works is you put in text, just say the cat in the hat. Or sorry, just say you put in the cat in the. And if it's a normal transformer, it would probably predict hat as the next word, H-A-T, hat. So, and it knew to predict it because it's seen that pattern so many times. So that's kind of how transformers work, as they predict the next letter. In this case, it would be the next character, but I mean in this file. But if you do the idea of the cat and the hat thing again, you might put in the cat in. So it would say, what's the next most likely word to come out? Probably the word the. And then it would take the cat in, the, that last the is what it predicted. It would take the original text you put in plus that word it predicted and use all of that as the new text, as if that's what you put in. And then it'll predict the next word from all of that, which will be hat. So that's kind of how transformers work. So come back down to here. This shows the train, validation, and test sequences. It says sliding windows per split. And this is for part of the idea of if you have just say 8 characters that it's looking at, or a certain number of tokens or words, whatever, then it's supposed to predict the next one. And so that's part of what the sliding window is for. This is just kind of an overview of it. This is for the embedding vectors, which is the characters in this case are turned into embedding vectors. Excuse me. The embedding vectors are what like the 64 that I showed earlier. So it says dimension. If I go up here, dimension 64. So it's the 64 numbers representing each letter in this case, or each character. So, found where I was on here. Okay. So here's the embedding. So this would be the vocab size. Looks like this, let's see, creates a random normal distribution. And okay, yeah. It's been a little while since I've looked at this file. I'm trying to remember what it's doing. So it's starting out, it's creating random numbers to represent each character. So remember I said it was 64 numbers to represent like the letter A, 64 to represent the letter B, a different 64, and so on. So what this is doing is it would be 64 numbers, but they would start out random from the random normal distribution. And this is to scale the numbers down so they don't get too big if they get exponentiated later. So, and this is the position vector, which helps to, one way to think of partly how it works is it helps to keep the letters in order and assign value, because the cat in the hat is different than putting the words in a different order, like cat that or cat, the, hat, in, etc. So the position vector helps keep the words in order, and that's part of what it does. And you can see that scaled down to one set of weights per layer. This is for doing that. Okay, here's the queries, keys, and values inside the attention layer. Remember, there's the transformer, and inside there, there's transformer blocks, also called transformer layers. And each of those layers consists of a attention, multi-layer perceptron, and a normalization layer. The attention layer has different attention heads, and I think up there it showed 4 attention heads for each layer. But each of those attention heads is broken down into queries, keys, and values. The queries can be thought of like if you're thinking of your friend's name and you want to call them on the phone. So, but you don't have their phone number, but you do have a phone book. So you think of their name, then down here you find their name in the phone book, and this is like the number in the phone book. That's one analogy I've heard of this, how the queries, keys, and values work. It's the actual calculations done are matrix multiplication, dot products. Dot products are basically batches of matrix multiplication is batches of dot products, or it breaks down to dot products, and dot products breaks down to multiplication and addition. So this is the I forgot what this layer was. It's been a while. And this is what this part was. This is the weights 1 and weights 2. I believe these are for the multi-layer perceptrons, because the main calculations, inputs times weights plus the bias, and then you have sometimes you scale it and you put the values through a nonlinear function such as rectified linear unit activation function or hyperbolic tangent or whatever. So, okay, then you come down here, and this is combining the different stuff together, or it's putting it into a list, rather, because this is, if I remember correctly, this is taking the embedding and position, and then it's adding to that the query weights, key weights, value weights, the WO, I forgot what that was, and the MLP weights 1, MLP weights 2. And then this iterates through and says that it requires grad so that it can keep the calculations and all that for back propagation to figure out the partial derivatives and so on. This is the normalization that I was talking about. In this case, it's the RMS norm, or the root mean squared normalization. And this one's the forward pass of the transformer. This is I believe that's batch by time. The batch by time, I believe that's what that is. It's been a while since I've looked at this file. I'm trying to remember what variables names are used for what. Okay, so then this is the embedding vector. Remember, a lot of this stuff was set up previously, and now this forward function, it's actually where the calculations are being done. Like up here, this was getting the stuff ready. I believe it was. Yeah, about 80% sure. Okay, so anyway, back to what I was saying. This is... This is the embedding of the characters. Like the characters, whatever you type is going in here. And then it's converting into a vetting vector. So if you put the word, cat, then it would take the CAT and it would get embedded in the C would have 64 numbers representing it, the A would have 64 other numbers representing it, and the T would have 64 numbers representing it. And this would also do that for the step that goes in. So what this will do is there's two types of transformers. There may be others as well, but one of them is the one that you don't want it to know the answers to while it's training, because it's supposed to predict the answers. And then it sees how far off it is and then makes adjustments based on that. So what this does, it's part of canceling out the answers so it doesn't know what they are. Because it creates a triangular, I believe it's called a triangular matrix, where you could picture a triangle going down through a matrix, or something going down from the top left to the bottom right. And I believe it's everything above that to the top right is zeroed out. Or it's either bottom left or top right, one of the two. But anyway, it's zeroed out so that it doesn't see what the answer is. And let's see. Okay, now down here, for layer and range, number of layers. Oh, this is setting up the stuff for each layer. Remember, there's, what was it, 4? I think it was 4 layers in this transformer. Let's see, layers, number layers 4. Yeah. So that's what this is doing, is it's doing the root mean square normalization, the query key values. This is where the calculations are going on. The queries, keys. Okay, so this is the matrix multiplication for the weights. See, it says WK or WQ, sorry. That's the weights for the queries, that's weight for the keys, and weights for the values. And what it's doing is it'll take the normalized X values and it'll matrix multiply matrix multiply with the queries, keys, and value weights to create queries, keys, and values. Then this view, it's reshaping them. The view and transpose is shaping them into the number of heads. Remember, each transformer has, in this case, I think it was 16 heads per transformer, I believe. We calculated earlier. And then down here, this is, if you look up the attention's all you need paper that the transformer idea came from, then this right around here, I believe it's right here, is the main calculation that it shows. And it's the queries matrix multiplied with the transpose. In this case, it's switching dimension -2 and dimension -1. Dimension -1 is the end dimension on the right side, and dimension -2 is the one before that. It's switching them. And then it's dividing by the head dimensions square, the square root of the head dimensions, raising to a fractional power, or raising to 1/2 power or 0.5 power is the same thing as taking the square root of the head dimensions. So that creates the scores, and this is that masked thing I was talking about, the masked field, so that it doesn't show what the answers are to the transformer while it's learning. It doesn't show them initially while it's trying to guess, because if it saw them while it was trying to guess, it would know the answers. It shows them later, though, for the loss calculation. So, and here's the softmax to basically convert stuff to probabilities. Here's the transpose to switch the dimensions location 1 and 2 with each other. And this is saying organize it in away. So it's batched by time by dimension. And then this is the residual connection. It's basically taking the original x up here, or it's doing that, and it's adding to the result of these calculations. That's after it's matrix multiplied with this as well. So partly what this residual connection does is it makes the gradient, it calculates the gradient or the partial derivative stuff better and simpler, and it reduces what's called, or it helps eliminate the so-called vanishing gradient problem, where the gradients can get so low that they disappear. So if it was going to get super low and you add this number to it, then it makes it not get that low. And it's also less compute for it to get to the correct numbers as well. So then the results of that is also passed into root mean square normalization. And then you take that, the normalized x, and matrix multiply it with the weights layer 1. This is the MLP. Weights layer 1, pass it through ReLU, matrix multiply the results with weights layer 2, or weights 2 indexed at the layer, add the residual connection back to it, and that creates the x value. Then you pass that into the root mean squared normalization again to squish the numbers back down again so they don't get too big. And then you matrix multiply that with the embedding transposed, because the embedding converts it to a certain way, and then the transpose, I guess it undoes it is a way to say it. And that x becomes the results of this matrix multiplication with the embedding transpose, the x matrix multiplied with the transpose of the embeddings. Then it returns x. So that's for the forward. And then go down here, and this is the loss. Let's see, eval loss, the evaluation loss, and f dot cross entropy. So the cross entropy, or categorical cross entropy, it consists of the negative natural log of the target class's softmax output, and it can be done in batches, and that's why it's here, it says divide by the number of batches. So, and it'll return the total loss, which is a number, and then the neural net can compare, it can see how far the loss is, and with the gradients from earlier, when it said requires grad equals true, right here, it can go back and see by using the chain rule, which is basically multiplying local gradients together, to see how each one of these leaf nodes affects the end result of the loss. And then it can make changes based on that. Changes to each of these leaf nodes, to the weights for the queries, weights for the keys, weights for values, weights for whatever that was, weights for the layer, the first layer for the MLP, and the weights for the second layer for the MLP, and the embedding and position. Yeah, the embedding vector and the position vector. So, and when the embedding vector and all that passes through the transformer, that's the residual stream. And if you hear the term residual stream, so you can picture it sort of like a boat passing through a stream, and it's trading goods as it goes down the river, and its goal is to keep doing win-win trading such that once it gets to the bottom, or keep doing trading such that once it gets to the bottom of the river, it has the highest value. In this case, the value is its ability to predict the next token correctly. So now here, that's the evaluation loss. That was the cross entropy. So this is forwarding the things through, and then it'll calculate the cross entropy loss, return it. Let's see, raw forward equals forward. Where's forward? See, forward's up here somewhere, I think. Or maybe not. Anyway. Okay, so down here has attribute torch.compile. This is for making the calculations more efficient with torch.compile, because you could picture the data doesn't have to make as many trips from the RAM to the graphics card RAM, the VRAM, so it can basically group the stuff together better, if I understood it right. It's like sort of like a truck coming from a warehouse to a grocery store. They could carry one item, or they could carry one pallet, or they could load up a bunch of pallets at once, whatever the store is going to need, and it would be a lot more efficient that way. So that's what the torch.compile, I believe that's what that's for. It makes more efficient trips to the graphics card for the computations. So it says it has attribute torch compile. Let's check in if it's using torch.compile, or if it's available. And if it is, then it's using it. Then the opt is optimizing the neural network. This is where it's actually doing the back propagation and passing in the learning rate to adjust the different parameters and to decrease the loss. So down here, that's saving the weights and the different things so that the file can be opened up again after it's trained, even if the computer is turned on and off, or turned off and then back on. And then that would load the weights through here. Well, this saves. This loads the weights once it's saved. And here's where the training loop is, so it can pass the data in. And it has plots to show stuff and so on. And let's see, train, sequence, batch, etc., cross entropy. I have some mechanistic interpretability stuff in here too. This may be part of that. I'm not sure though. Let's see. Evaluation every 10. Okay. Anyway, that's part of how a transformer works. And if you have any questions or comments, let me know. And check out some of my other videos that goes into details about how multi-layer perceptrons work. And check out the one where for the MNIST that I wrote from just memory without looking up anything. I go through in detail that one a while before. It's I went through it like 50 times, I think it was, to practice, and ended up writing it, I think it was multiple times just from logic and memory. So, yeah. Real quick, down here, this is an example of it's completing the next token. So if I put FIRS, then based on what it was trained on the Shakespeare stuff, it should predict T as the next character. So, but if I put FIR, well, I would test this out, but this is in the GitHub, on my GitHub, and so it's not on Jupyter Notebook currently, right here. There's not I don't see a place to hit a button and make it run. But it trains on, I think, relatively low compute according to what batch size and how many dimensions and so on it's set. But if it's set too high, then it can overload like if it's on CPU, it can overload if it's set too high and so on. But if this said FIR, then once it passes into the encoding, turns into tokens, then outputs, let's say the tokens goes here, and patch or it would put the tokens, it would convert them to a tensor, and it would pass those into the forward, raw forward that we saw at top. And see if I can find it again real quick. Raw forward is right. Well, that's forward. Is that different than raw forward? Hold on. Forward raw. Forward. I might have changed one of the names or something. Anyway, it passes it through the forward pass, or puts it in for the forward pass of the neural net. Then, so if you download this, I'll probably leave a link to it in the comments or in the description of the video. If it doesn't work, part of the reason might be because it looks like I changed the name forward to raw forward down here or something, so you can just change the name back or whatever. So anyway, it goes through the forward pass, now it puts the logits, which is the raw predictions. Then this is the softmax, which converts those raw predictions into likelihoods or probabilities. Then those probabilities go into the torch.multinomial, which takes that probability distribution and it randomly picks based on the probability distribution. And that way it's not always the same characters that pop out with the same input. You can adjust it to be that way though, and then this is the loop that I was talking about in the appending, or taking the previous input and the prediction and then using that as the new input. So just say if you put in FIR instead of FIRS, put in FIR, and then it predicted the next token was S. This is technically not in characters currently while it's doing this, but because it decodes after that back into characters. But just say if I put in FIR and it predicted S comes next, then it would take it would take the S and it would append to the FIR, so it would look like that. Is one way to think of it. Then it would take the FIRS, pass it through the raw forward, output the prediction, and it might be the letter T. So this is set to 200 iterations, so it would take that FIRS, or it would be up here, and it predict the next character would be T, the next token is T, so that appends or attaches it to the end of that FIRS, so it would then become FIRST, and it would most likely, since it's 200 iterations, it's only gone through 2 iterations so far, then it would probably figure that a space is next, so it would predict space is next, then it would attach that to the end of FIRST, and then it would predict the next and the next and so on until it got through with the 200 iterations. So that is how a transformer works. And that's quite a bit of it. So if you have any questions or comments, let me know, and check out some of my other videos for more details on the multilayer perceptrons. You can check it out. The MLP video is I think it's the MNIST from scratch video or something like that is title on my channel. So thanks for watching. Please click like and subscribe, and let me know in the comments what you'd like to see. Thanks.